Okay, I left off in our lecture about the two-tube model with conundrum, um, about how we can possibly get formant frequencies which are lower than 500 hertz, which is the lowest formant frequency you get when you produce a schwa, which is based on an open tube of length 17.5 centimeters, or about 7 inches. So in the tube model, the idea is that we're splitting up the vocal tract as a whole into two shorter tubes. So each of those tubes should have higher resonant frequencies than the overall length of the tube. So we've mentioned in the past that in theory, if you round your lips, you are kind of lengthening your vocal tract a little bit, maybe about maximally, I'd say an inch or so, probably even less than that. So it's a bit of a stretch to say that that's going to produce huge changes in formant frequencies for a vowel you're producing, but you can hear them when you do that. It's like, you're able to change the formant frequencies a bit there. But what you do not do, so let's take, for instance, an E, which is a nice high vowel, and oftentimes for a speaker like me, my F1 for E is going to be about 300 hertz. So that's, well, 250 hertz would be a frequency which is half of 500 hertz, that F1 for schwa. To get to 250 hertz with just an open tube, open unperturbed tube, I'd have to have a vocal tract length which is about twice as long as I normally do. So I can round my lips like that, but I'm not going to be able to extend my lips to be twice the length of my entire vocal tract. My lips don't come out for 7 inches in front of my face, right? Or even 6. Maybe just a little bit further than normal. So how do we get that low first formant frequency for a vowel like E, a high vowel like that? We take advantage of a different physical phenomenon known as a Helmholtz resonance. So this idea or this concept observation comes from a famous German acoustician named Hermann von Helmholtz, who lived in the 19th century. And he's an interesting guy. He was a university professor, not unlike myself, and he would teach during the day, as was his job, as you might expect for a professor. But then at night, when he was done teaching, he would stop and think to himself, well, is what I said today in class actually true? And then he would do experiments on the side, and he kind of pioneered the research tradition in institutions of higher education, which is now effectively our primary job, which is to do research and then teach on the side. So he kind of flipped the script there a bit and created the future. And so what he got out of his research, one of the many things he got out of his research, was this observation that a tube that has a narrow constriction at one end forms a different kind of resonance system than the systems we've looked at heretofore. So the air in that narrow constriction will exhibit what's now called a Helmholtz resonance after Mr. von Helmholtz. And that narrow constriction is going to vibrate back and forth like a piston. So I've actually got an example here. I've shown this before in 341, but it's going to be a Coke bottle. And I've got a little diagram here which shows something that looks a little bit more like a wine bottle. But the idea here is that you have a kind of larger cavity at the back end of your resonator, and then there's a narrower cavity here, kind of close to the open end. And this air pocket, which is in the narrow passageway here in the resonator, is going to vibrate itself back and forth like a piston as you kind of send sound waves through the entire resonator. So we can kind of calculate a resonant frequency based on this length by itself, but then we have to calculate resonant frequency in an entirely different way for just this part of the resonator. And that frequency is going to be pretty low. In a Coke bottle, it's not quite the same shape, but it would be something like in this region here where you get that sort of Helmholtz resonance. And I'll try to give you some demos here in a second. We can walk through the math of this just in principle. This is more math than I expect you to really be comfortable with for this class. So we'll just try to think about it in general terms without having to walk through the specifics of the numbers for any particular configuration. But let's say we have a setup like this. This is producing the vowel E. where we have a narrow constriction here, sort of at the front of the palate, maybe even in the postalveolar region. And then, so there's a little bit of a tube here in front of that constriction, and then there's a longer tube in the back. So normally what we would think is, if we're just splitting this into two tubes, we have this long tube here, which should give us one resonant frequency, a relatively low resonance, maybe not 500 hertz, but somewhere around there. And then we have a short tube here in front, which would give us relatively high formant frequency, right? Because it's only maybe a couple inches long or so. So if you kind of plot this out in a two-dimensional representation, it sort of looks like what we just saw on the previous slide, where we have kind of this longer tube here, and then it narrows through this little passageway. And then kind of the addition here is that we also have this front tube, which is more or less closed at the back and then open in the front. The crucial part is this little narrow passageway here. And if we look at these variables here in the equation, which gives us the Helmholtz frequency, it's got a few variables specified on the basis of this BC passageway. So ABC here in the numerator of this fraction is the area, the cross-sectional area of this little Helmholtz resonator. The LBC here is the length from B to C in the same section of the entire setup. And then VAB is the volume of this back tube, or this back resonator here. C is still the speed of sound, 2 pi is a constant, and then F is going to be our formant frequency for the Helmholtz resonance. Okay, so you can kind of think about this maybe in general terms before I show you the math, but this is going to depend on the length of this guy. So the longer this stretch is, the lower this overall value would be, because if we increase the values in the denominator of this fraction, the whole thing is going to go down in value. The bigger this volume is behind the constriction, the lower that formant frequency is going to be as well. So we have a pretty large cavity here in the back, so it has a lot of volume that would kind of drive this resonant frequency down. The cross-sectional area as well, the smaller that gets, the lower the resonant frequency is going to be. If you open it up a little bit more, that's going to make it a higher frequency, right? I'll show you what the math looks like. This volume, if it's 60 cubic centimeters, these are examples I got from a textbook on the subject. You don't have to memorize them, you just kind of have to understand how they could fit together. Let's say the length of that constriction is about 1 centimeter long. And then the area, the cross-sectional area of that constriction is about 0.15 squared centimeters. So if you actually run those numbers, you wind up getting a Helmholtz resonant frequency of about 280 hertz. This is a potentially realistic example. Yeah, so I'm sorry that the formatting of this got messed up. I had to upgrade formats for this PowerPoint slide. I think you can still read it, so I'm not going to worry too much about it. If you plot this on the same sort of nomogram that we have been looking at before, then the Helmholtz resonance is basically going to be primarily independent of what else is going on based on those variables we saw in the previous slide. But it'll look like this. It'll have basically a consistently low resonant frequency throughout that'll almost certainly form the F1 for this system. And then the other formant frequencies can be calculated in the same way, looking at the front cavity resonances and the back cavity resonances, but they're always going to be at least F2, basically. Okay, so just to kind of show you what this looks like in reality, not that we haven't seen an E before in spectrogram land, but this will give us kind of new insight into it.
Heed.
Yeah, and so
Heed.
There's F1 for this guy. It's about 360 hertz. So again, the reality doesn't match up with the predictions exactly. It's a little bit higher than we might expect, but there it is. That's the Helmholtz resonance, and these other resonances or formants are produced by the other tubes in the system. I didn't actually give you the demo I wanted to give you. I went through some trouble getting these pop bottles, and I know I've shown you this before, but we've got 2 pop bottles. I'm going to open them up and then try to blow across the tops so that they resonate. I've been practicing. We'll see how well it goes. But if it doesn't work, I'll refer you to another video where I succeeded. Anyways, because why bother recording this again? Anyways, the idea here again is that this is sort of going to give us a Helmholtz resonance here, this narrow passageway at the top. And so that's the length of that stretch is going to be consistent, basically, as well as its cross-sectional area, because I've reduced the amount of pop in both bottles to be behind that resonant passageway. What will differ, though, is sort of the volume behind it. So there's basically going to be a larger amount of volume in the bottle behind that constriction here, because there's less fluid in it than there is here. So because this volume is bigger here in the denominator, we'd expect the overall resonant frequency to be lower for this guy. Let's see if my prediction holds true. Let's see if I can get this to work. Okay, that wasn't too bad. Horizontal. There we go. All right, so we have a lower resonant frequency here because it has larger volume behind the constriction. All right, the key is, like I said, creating turbulence across the top of the bottle. But you gotta practice. But I guess I'll mention as well, this is basically, there's turbulence when the air flows across sort of the lip or the opening of the bottle, and that forms the source of the source sound for the entire system. So this is sort of like having your glottis vibrate at the back of your throat when you speak, except the turbulence isn't picking out specific harmonic frequencies really, because it's not periodic, it's just random turbulence, random noise. So you kind of get energy all across the board, across all frequencies, but the resonator back here is still going to pick up on the ones that it likes best, and those are the ones that are, that's the frequency that's going to sound louder. If I actually ever get that to work. I should have quit while I was ahead. But that's what's going on. The source is just me creating the sound, and then the filter is what is happening in the Helmholtz resonator behind it. Okay, all right. So you can review the video if you want to watch the glory of me getting that to work properly, or maybe I will. You can move on with me for the meantime to the next slide. So again, this is trying to just walk you through the concepts here. Like if we move this a bit further back, what would happen to our Helmholtz resonance based on what we just learned? Let's say our length stays the same for this constriction and the area stays the same, but we move the whole thing back, then this volume should become smaller. So we'd expect this overall equation to become higher in formant frequency, right? So we're lowering the value of the denominator. That makes the whole fraction bigger, or produce a larger number, I guess you could say. So the frequency is going to be higher if this is more of a, say, velar constriction rather than a palatal or post-alveolar constriction. The trick is, though, that it gets more complicated than that. So that this would sort of be like, I guess, moving from like an E to an U type vowel, an unrounded high back vowel. But normally, we actually produce an U, which has rounding at the front of the vocal tract. And when you produce that rounding, you're actually getting a second Helmholtz resonator into play because you're creating two narrow constrictions when you produce that vowel. So you are producing Helmholtz resonator here at the velar region, more or less, and then you're producing another Helmholtz resonator here in the front of your vocal tract by rounding your lips. And each one of those is going to have an opener sort of cavity behind it, and by sort of forcing air to flow through this whole system, you're going to create two Helmholtz resonant frequencies. Both of them will be pretty low in frequency, which is how we get sort of the characteristic acoustic pattern for an U, right? There's one Helmholtz resonator, there's another. There's F1 and there's F2, it turns out, because this one has more volume behind it. This one has a smaller chamber right behind it, so it's not going to have a resonant frequency that's quite as low. I actually got all these diagrams, the nomograms and this particular diagram as well, for the Helmholtz frequencies from a classic text on acoustic phonetics by Ken Stevens, former professor at MIT, who was kind of an engineer turned into an acoustic phonetician, or phonetician in general. So it's really great. It's really thick, very technical, very detailed, kind of written as you might expect an engineer to write a textbook. So it goes well beyond what we talk about here, but it's got a lot of great stuff in it that we kind of have borrowed to provide us with a basic understanding of acoustic phonetics. So most of the math that we get in this lecture is from that textbook. It's funny though, because like I said, it's very detailed, and he's happy to kind of dive into all the nitty gritty for how these things work. But when he gets to this point with a configuration that's going to produce two Helmholtz resonant frequencies, he basically says, well, the math is too complicated for this book, so I'm just going to skip it. So if it's too complicated for Ken Stevens, it's definitely too complicated for us. So hopefully you'll just take my word for it that this system just produces a very low first and second format. And we can go from there because this is how we get two Helmholtz resonances. Let's look at another aspect of this equation. So what would happen if we opened up the constriction, i.e. increased its cross-sectional area, which is this variable in the equation? As you might expect, if you sort of go, like opening up that constriction, you're going from like a high vowel in the traditional form or traditional vowel space to a lower vowel, right? Like E to A. You're opening up your mouth. You're increasing the cross-sectional area of the whole thing. Because this number is getting bigger, you'd expect the entire equation to yield a larger number. So frequency should get higher as well. We'd start off with a low first formant frequency, which is characteristic of high vowels. And then as we open it up, our F1 goes up as well, and we're getting into low vowel territory in our typical vowel space chart, right? So that explains why there's a connection between F1 and what we normally think of as vowel height, or how open the vocal tract is when you're producing a vowel. Okay, so that's about all I'm going to say about the two-tube model for now. At least in this little segment, we'll talk a little bit about how it relates to music in the next one. But like I said, there are kind of trade-offs in terms of which theory you'd prefer to use, given what you're trying to explain in acoustic phonetics. So perturbation theory and the two model don't always make the same predictions, and it turns out that each explains some vowel facts better than others. So we talked about this with perturbation theory, but sometimes when you have more than one constriction, like ooh and it seems like the various constrictions are kind of working together in synergy to produce the same acoustic effect. And for that model, which is relatively complicated, but you can kind of easily see the connections between the multiple articulations and why they're sort of both being employed to produce the same acoustic pattern. So that theory makes those connections easy to see. But the two model works a lot better for one constriction. Like even for ooh, it was too complicated kind of for Ken Stevens to walk you through the math of how you can use that model to predict the formant frequencies for this vowel, but for perturbation theory, it's pretty easy to see the connection there between the labial and the velar constriction. So you kind of want to stay away from that with the two model, but the two model also, it works better for relatively constricted vocal tract where there's less acoustic coupling, and like I said before, you can make predictions about what formant frequencies you'd expect with the two model because the math is like nice and clearly laid out. Which you can't really do as easily for perturbation theory. You just get sort of general predictions there. So I'm going to stop now because the music part of this is going to be a bit of an addendum to this lecture, but I'll head to that next right after the break.